kept in touch. His area actually, can I say robotics? He has his PhD from Carnegie Mellon University, and he worked on robotics and related issues for many years. And now they have one of these centers like ours, but the larger one joined with Carnegie Mellon, Ohio State, and University of Pennsylvania, and they're working on many things that are very much interest to us, like autonomous vehicles, safety, and planning of these different technologies. So with that, I will leave Rahul to talk more about what they're doing, and I'm looking forward to hearing very exciting new research.
Cool. All right. Thank you for having me here. I'm obviously here just for the cookies. So, so so I have a question for you all, right? I mean, you're obviously the wrong audience for buying a Tesla, but let's just, if Tesla is giving a free Tesla, how many of you all would want one? And so you all don't want a free Tesla if it's free. But you have to drive it. I mean, you have to use autopilot in that, right? You have to use autopilot to drive around, and so in a normal sort of general public audience, usually you see like more than 90% plus people raise their hands, and so let's try to look at a couple of things in terms of how these Teslas are driving, right? So this is an example in in Switzerland, and that's like a slow thing, right? So I think I need to share my sound. Just give me a second. I have to.
What's the sound?
Yeah. Okay, is it?
Is the sound for the TV on?
Or the conference? Okay. So that's a slow accident over there, right? So no big deal. The car in front just suddenly moved aside, and gradually moved aside, and then the next sort of just give me a second now.
Is this mode level 3 or level 4?
So these levels are really the confusion that one person's level 3 is another person's level 4.
NHTSA level 3 or NHTSA level 4.
So this is in Tesla autopilot mode, right? So this is whichever level you want to bin it in, I would say, because you still have to keep your hands on the wheel. Now, who's making the decisions? How are the choices being made? It's kind of in between level 3 and 4, but somewhere, right? So a different sort of effect would be with so we can look at like something little bit faster. So this is again in China now, and then the car is again similar situation, and then the Tesla scrapes the other car, and then you see, okay, fine. This is again nothing bad really happened, but there is some audio over there, but I guess it's not. I don't know, for some reason this is not working, but so then comes like a faster case over here, and then this is in so this is like a vehicle going at about 55 miles per hour and a 24-year-old girl dies on the spot over there, right? And then but you can see it's a pretty clear road. It's not I mean the video is blurry, but actually it's the car can see that sort of thing. It's just you can see it from several hundred feet away, and so then most people say, oh well, this is in China, right? What's the big issue? I mean, it's not happening in New York, and it's not happening in Texas. Then we don't have to worry as much. But the problem here is that this is a systemic problem, right? It's the same driver that's driving in China versus driving in the US, and then Elon Musk or someone from Tesla would say, well, that's an isolated incident. We have updated our software since then, and software version 7.2 will be, it's much safer, right? So these are like just an example of problems that we look at, as part of our Department of Transportation National Transportation Center. So I serve as a Penn director for that center, and this is between like 2017 to 2022, and it's a $14 million collaboration between CMU, Penn, and Ohio State. And this is our third such center that we've been working on. And the general sort of overarching theme is, safe and efficient movement of people and goods, right? So so the goods part is just as important to us. But today I'll just talk about one particular question that we are trying to answer, is that if you have these driverless vehicles, what would be a driver's license test to know that what is safe over there, right? What is safe, what is unsafe? So many of us have got. How many of you all have taken a driver's license test? And then the others are transit people. So we are all. I'm a fully transit person. Okay, so whenever you did your test, it's like 15 minutes. You had to wait for 2 hours. You got a 15-minute test. Now you can drive for the rest of your life, right? And you have license to drive. And similarly over here, what would it be an equivalent for this sort of situation, right? So, but first we have to sort of ask the question that well, how do we define safety for autonomous cars? So when I moved after grad school from Pittsburgh to Philadelphia with my same old crappy car, then it just cost me 3 times more insurance for the same car, same driver, everything the same. It's just the environment was different, right? It's much riskier environment than Pittsburgh. But how do you actually think of safety? So then arguments are, well, let me ask you guys, what would you say is a safe enough AV? What kind of metric would you want to use for that?
Incident per miles traveled.
Incident per, so some sort of statistical way of looking at that, right? So, but what would you say also as being safe enough?
Human intervention.
Humans.
Intervention.
Okay.
Yeah.
So how many times a human is intervening when the vehicle is actually going to do something wrong, or?
Yeah, like after how long there has to be a human intervention.
Okay. Yeah. And that's something that, okay, so that's the when the human is sort of almost like saving the vehicle and themselves. What would be other metrics that
The highest level for the IHS level, the test.
but and how would you capture that level?
I mean, indoor collision.
So with you mean with crash tests?
Yeah.
But that's like it's the same. Let's just say it's a 5-star crash test rating vehicle, and now it's self-driving. So it has already got 5 stars, right? But what is the equivalent JD Power 5 stars of safety for this vehicle then?
Amount of scenarios accounted for?
The
Scenarios.
different scenarios and how it actually can go through these
Yeah.
scenarios, right? And so like a T junction, like a roundabout, merges, exits, and then statistically. So a lot of analysis and the statistics say that well, look, an accident happens every 100 million miles. Statistically, if you want to get a safety metric for a new kind of vehicle type, you have to drive about 100 billion miles to get a small enough p-value to get statistical significance. But here now these vehicles are being driven 10,000, 20,000 miles, or Waymo will say, look, we covered 8 million miles since we started Waymo, and that's the total number of miles. They're not going to get to 100 billion miles anytime close. Then companies like Qualcomm or Nvidia, they say, look, we did 10,000 miles, and Nvidia is based near Rutgers in Jersey, and then they say, look, we drove these 10,000 miles. It took a while for us to do that, but now we change the camera. You change the camera, you change the eyes, you change the perception system. You're basically changing the driver. And then they say, oh well, and then Waymo will say, look, when we have gone through about 24 software updates in the last 2 months, and every software update is changing the driver, so you basically go back to mile zero. So every time you're going back to mile zero with any of these changes, right, because the driver is changing, so it's very difficult to get any statistical sort of number, right, over there. So that sort of problem is a fundamental issue in what is safety, right? Safety has to go beyond being perceived safety in the way marketing is selling it today. But that brings us to like a more concrete problem that a couple of years ago, Toyota had come to us and they said, look, we can make these autonomous cars. We want to make a lot of them. But then the insurance companies have told us that, well, if we make these cars, driverless car, driver doesn't pay the insurance premium, you have the insurance liability and you basically have $1 trillion liability. And then the management came back and they were like, look, the more cars we make, the more liability we have. And that's not a good business model. We are not a liability heavy company. We just want to sell the car and get it out of our door. And we don't want like this airbag recall to basically implode our company like that, right? So that's sort of a problem over there. So then they were like, well, how can you bound and minimize the safety and the risk that these vehicles are bringing, and have some sort of way to capture this risk so that we can then make a safety case argument for insurance or for the municipalities that we are going. In fact, but we don't want to be driving like hundreds of thousands of miles and then starting with mile zero every time. So we want to be able to actually find the riskiest miles in the most efficient manner. So that's what we call the guardian angel problem, which is essentially what our research focuses on, is building a search engine like a Google search engine, but for the riskiest miles, right? The riskiest miles, the riskiest conditions, the riskiest scenarios that you're driving on, and being able to then provide some quantitative measure of safety in those cases. And a separate project, which I won't talk much about today, is on when you get it connected and autonomous, and that's like a new Intel center that is at Penn, where we really look at, well, if these vehicles start talking to each other, how does that quantitatively improve the safety of these vehicles? Because now if you're getting blocked, like in this Tesla case, you can't, even though your LiDAR can see over 200 meters, but the vehicle in front of you, it can't see through that. So if they're talking to each other, then now it's machine to machine, right? So if you look at now how these actually autonomous vehicles work, they have sensors, right? So they're going through this sense, plan, act, and they're doing this loop, about 20 times per second totally. And so, but in the sense part, they're getting like the RGB camera data, they're getting the depth sensor data, they're getting, and this is how far objects are. And like your Xbox Connect, this is optical flow data over here. And then they're also getting like object detection data over here. And then they're doing semantic segmentation, where they're saying, well, this is the drivable surface, these are surfaces that you can't drive on, and it's classifying objects, everything, right? So all of this is basically getting streamed frame by frame on the perception sensors and perception layer, and then it's fed to the planner, right? So a mission planner is like coming from Philadelphia to Manhattan. Use Google Maps, whatever, take NJ Transit, come here, right? So and then, so that's a long-term planner, right? So the behavioral planner is saying, okay, well, if I want to go from from Manhattan back to Philadelphia, I need to get onto I-95 South. In order to do that, I need to take this exit to get onto Lincoln Tunnel, or and so it is deciding that it's a discrete decision to make. Say you need to take this exit now, and in order to take this exit, the local planner, which is just looking ahead, say the next 100 milliseconds, is saying, well, these are the possible trajectories that you can use. Pick a trajectory that has the best, best sort of best cost metric for you along this, and then you need to follow that trajectory with the control, right? So and the control is just your steering angle, acceleration, and brake, right? That's it. So all of this is going down to just steering, acceleration inputs. And so the planning is trying to decide, well, what to do in this scenario, what to do in each situation, and it's a discrete decision that is being made over there, right? So we have this decision maker over here. Where the vehicle, as it is driving now along the way, it has to make either like it's doing a lane follow over here, and it keeps repeating through that, or it goes through lane change, then it has to decide when to make a lane change under certain conditions. That's like a discrete decision over there. And this vehicle is also has some continuous dynamics, right? So where it has its own steering angle that it can go through, it has its own inertia, and the control system of the vehicle can't make it do a 90-degree turn. So it has its own continuous dynamical constraints that you have to take into account, right? But then there are also different rules for safety or for traffic, that it has to maintain a speed limit, has to maintain a buffer, it has an objective to basically get into the left lane and then make an exit from there, and so on, right? So these all have to be captured in some model now. And as you can imagine, that model is going to become quite big and unwieldy. And so, say for example, this vehicle is trying to make an entry onto the highway, and then it has to maintain some, that's pretty risky entry over there. So it has certain rules. If it slips, it recovers in 3 seconds, stay within lane markers, maintain within minimum distance. So all these have to be encoded into a useful model for the system. Right? But now you can model all you like, as you guys know, that but in reality, things are always going to deviate from that, right? And so the actuators, for example, on this vehicle, you could have modeled it, but they are slower than you modeled it in reality. The road that is driving on could have black ice, and then the vehicle skids, but you just you can't model reality in totality, right? So the other agents that are not in our control, they could be like Boston drivers, right? And then more aggressive than you model them to be. But now, how do you handle all of that, all these deviations from your model? And so if the car now was supposed to take this trajectory, but it skidded, went off, but it recovered in time, and now it's entering the on-ramp, but with a different angle and a different speed or velocity over there, is that unsafe, right? I mean, it did do what it's supposed to do, but it's not doing exactly according to that original plan over there, right? So then what is safe and what is unsafe, right? And how do we sort of go between this binary? And do we look at each case? Do we look at how things are deviating from our model? And so is this unsafe? I mean, these are pretty close. It's a pretty aggressive exit over here. And then is this more unsafe over here as it gets closer to the other vehicle? So we have to think of safety not as a binary, but more as a continuum, as a spectrum of safety, rather than just safe and unsafe. And we need to have some sort of quantitative continuous measure of safety, because these situations of near accidents or almost accidents or things leading to an accident all have to be quantified within that framework, right? So, but this forces us to now refine our question of, does the autonomous vehicle satisfy its design requirements for safety, to how robustly or how well does it satisfy these requirements, because you're operating across a range of different conditions, range of road topologies, range of weather conditions, a range of other driver behavior. So we want to look at this on a continuous scale of safety where we quantify it into this metric called robustness, where if you have a model and the world and anything that deviates too much from that model, where the model disturbances to that model basically invalidate the model, right? And then you or invalidate any verification results that you have to a model that can be more robust. That means it can tolerate a large amount of disturbances, large variations in actuation, in other agents, in the way it is the drivability of the vehicle. Then that's a much more robust model. It's just saying that it can tolerate so much more deviation from that, right? So many of y'all would have heard of this Tesla accident that happened back in the summer of 2016, where this truck trailer was making a turn, and this oncoming car driving in autopilot could see this truck from very far away, but it just went through it, right? And then it went underneath, and then in autopilot mode, it went off the road, broke through a fence, hit a power pole, fell into a ditch, and so again, I'm not against Tesla or anything. It's just that they have the most examples. So it's not like we are picking on them, right? I mean, who else do we pick on, right? So, I mean, GM is just like disbanding half of its plans on electric vehicles. So I think people are struggling to get into that. So So, but this is autopilot now, so then we can sort of look at this. If there was audio, there's some nice audio. So we have our Tesla over here. Maybe I'll play the audio from my laptop later on. But the idea here is that we can change the weather, the lighting conditions, but it's not just to make like a pretty video, right, with Grand Theft Auto. The key point is that as this vehicle is coming through, we can extract from the depth buffer what the vehicle sees like a LiDAR map. It's pretty much the same thing, and that's sort of what the vehicle is seeing as it's driving there, right? So, then this vehicle, from this vehicle's perspective, we can extract LiDAR maps for these very hyper-realistic environments and use that as virtual sensors over here from any perspective, right? And in fact, then we can do all sorts of different processing on these different depth maps, point cloud maps, and object detection as this vehicle is coming closer. And we can mount as many cameras as we want on these virtual vehicles now and drive them through hundreds of thousands of miles over here. But as we are getting all of this data, we can then run online, uh, you know, uh, capturing frame by frame of the simulated camera, extract the depth map, and then do a semantic segmentation, and then do simultaneous localization and mapping of this vehicle as it is driving through these cities over here, right? So then the question is, well, how can we use this, right? If we can drive through hundreds of thousands of miles, in this synthetic world, then we can actually, on top of this, we built a search engine to say, well, run through this synthetic world and keep giving us the most dangerous situations to that, right? So for example, here is a very sharp high-speed turn, and where the vehicle is, could be going out of control, and then we can actually drive this car now with the front end where it is getting frame by frame on a machine, but it is also plugged into like a third party's perception, planning, control system that is basically getting like almost like bringing a car, mounting it up and making it wear VR goggles, and it's actually driving through the game, but it is using its own perception, planning, control pipeline as it's driving through that. So in fact, in this case, we had the simulated world running in Philadelphia versus the whole pipeline was running in Boston, and was sending frames across and driving this car step by step, right? So we can even incorporate like end-to-end like machine learning using convolutional neural networks to basically take these frames and determine what steering angle and acceleration you would have, and then we are running this for hundreds of thousands of tests, right? So now, and this is one of the tests that gets returned and says, well, this is a test where the vehicle actually failed to satisfy its safety constraints, which means that the vehicle really crashed, right? So, but the whole point here is that we can go through as many of these crashes as we want before the vehicle gets on the road, right? Because we are running these tests for the vehicle in a very large scale. But we are not doing this just exhaustively, right? Or we're not just doing this in a simple Monte Carlo fashion. We have a specific way of actually identifying this in a gradient descent fashion. So where we have all of our simulation parameters for the model, and then you can plug in like a third-party AV black box code of their perception planning system, and that is basically providing the steering and acceleration, and it is capturing frame by frame of this virtual world. And what we are controlling now is what are the conditions the vehicle sees, who are the other agents, what is the weather conditions, and so on, right? So this is our AV CAD or AV computer aided design testing interface, where here we can have, this is just testing the T-junction scenario. And so we are varying the lighting conditions, we are varying the initial speed and position of the vehicle that is coming across at the T-junction, and running it through many of these iterations, but then smartly searching for where this is going to be very safe versus where it's going to be very unsafe, to where it is also in this borderline situations. But we can pick different scenarios of merges, highways, off-ramps. There are many different scenarios, and then you can have different settings for initializing the scenarios, different AIs for the other agents, and then you can change weather options. But the most important thing is that you have these specifications of safety, right? Time to collision, how close does it get, and how risky is it. So these are all metrics that we can capture symbolically, and then this system is now trying to see when do these specifications get violated, and it is doing this in a very fast and smart fashion, right? So we are not just going through that exhaustively. So, but if you think about it, like the NHTSA has this report from 2013, which looked at over 6 million vehicles, and they could bin more than 99% of the accidents in terms of the frequency, severity, into 35 different driving scenarios. These are, of course, of human-driven vehicles, and so we can take these different driving scenarios, and we can start to model them, like over merges, overtakes, T-junctions, roundabouts, exits, all of that, right? But then we can run these now with different initialization points and exhaustively search across a range of distributions, right? So this is one example of a vehicle trying to make an exit, and then it spins out of control. So here the point is that this is not manually made by anybody. This is something that is returned by the search engine to say, look, here's a violation. This vehicle failed to satisfy its objective of getting out of the exit, and then we can go and analyze that, right? So here, and then when we analyze this, we can look at the decision tree over here of how the vehicle is making its decisions, and then we can interpret and point out that this vehicle moved from its highway speed controller to its exit controller a little too late, and therefore it was going in too hot. But that is our interpretation. But the point is that this issue could be with other vehicles, with the weather, with the road network topology itself. It could be with the dynamics of the vehicle. It could be with the decision making of the vehicle. It could be with any part of this model, and we can identify that portion. And the way this search engine works now is that it returns a robustness value. So any value that is very negative, you can then click on that value, and then it will procedurally generate a video of that scenario over there. And you can actually see that, because our partners in Toyota at that time were like, we need to see a playback of a failure. And then we had a different problem with them, that every time we showed them the failure, then a different failure, they would be like, oh, okay, we understood that, now it's very obvious. Show us something that's not obvious. And then this became a really difficult thing, that once you explain something to someone, it becomes obvious. Then how do you show them something not obvious? And every time we explain it, they say, oh, that's obvious now. And then what's not obvious? So then we can take this vehicle and run it in more high fidelity simulations. This is for looking at a local planner, which is looking at about 100 milliseconds ahead. And these are all the splines of possible splines, and it is picking this spline over here to follow this line across. And then we test our vehicle. So this is an example of a test of a real vehicle in Nagoya in Japan with one of our partners, where we rented out a lane, and then we are driving it and to test out this local planner at that point. And so then it's sort of going from this simulated land to high fidelity simulations with dynamics into real vehicles, where we can now sort of gradually get to certain safety benchmarks as this vehicle is getting onto the road, like that, right? So in terms of how do we do this, right? So if we look at, so we use this approach called this logic called metric temporal logic to capture all of these questions over here, right? So of all of the dynamics. So we can set the initial, like we can set the lighting conditions to be within a range. We can set the initial positions of the vehicles. We can set the initial speeds of the vehicles, all to be within these ranges. And now we're going to run these simulations and then search through under what conditions does this vehicle start to violate any of its specifications, right? So we can choose we can choose all of these settings within some ranges over here, and a set of actions also within a range of actions. So these are like kind of initial points of where the vehicles could have started, and there would be initial velocities of these vehicles. And so say for a T-junction case, we can then specify, look, we want to be able to search across all of these ranges for each of these dimensions, right, in terms of how the other agents work, how we work, and what is the goal of this of the scenario. I'm going to capture all of that in this logic. But what this logic essentially is trying to do, say for example, we are saying what is the distance to another vehicle, right? So if we get, this is the other vehicle, and if we are getting closer to the other vehicle, this is one simulation run where we are non-deterministically choosing the range from a point within that range to initialize that run. So it could be the other vehicle speed and our vehicle speed at the T junction, and then we are running the simulation through that. And then this is the closest it comes to that other vehicle. And so we basically treat this tube over here of the distance as the robustness value. This means that if this scenario was actually disturbed by this much, then this is the amount of disturbance that we can handle until the safety specification is violated. And then if we have another simulation run that basically is this blue line now, then we can see that this is getting closer, so it actually has a lower robustness of that. So but anything that is within this robustness tube, and all simulations that run within this robustness tube, they all basically can be eliminated to say that, well, they have this amount of robustness, this quantified amount of robustness before it violates the safety constraint. And so then we can say, well, all of that can be treated as safe. Anything that comes out of this robustness tube, then whether it goes back in or whether it crosses that, that safety constraint over there, that is something that we cannot determine with this testing method. So anything that is within this tube, we can eliminate. We can just say this is safe or this is totally unsafe, anything that's violating. But what we cannot answer here is what are things that get out of this tube and they may come back or they may not come back into this tube. So essentially what we are trying to do with this testing approach is we're trying to eliminate all things that are safe. And this is the entire search space, say of my speed, other vehicle speed over here. And this is the robustness, this is the basically the size of that tube. And I'm removing all of these scenarios that I'm testing against and saying, well, this is so robust, I don't have to test any other points here. I'm going to just remove it, because what I really want to find out is what are things as I get to being more unsafe. And what I can't determine with testing is these corner cases or these boundary problems, which are where the robustness is low, it is getting close to the unsafe situation, but I cannot actually give you a clear answer by just testing. So then we have to run that through a system called Reachability Analysis, which is basically like a formal verification tool that can exhaustively search that space. But essentially those tools can only work with very small ranges and smaller problem sizes. So we are essentially eliminating most of the search space and only determining what is this boundary of safe and unsafe for the T-junction case or for the roundabout. And so for this T-junction case over here, we can then run these tests, and anything that's green over here, we can basically say all these are safe in terms of the position of the vehicle, the velocity of the environment vehicle as it is coming on the T-junction. And then we really want to focus on these cases where safe and unsafe are mixed. These are the boundary cases over here. And so that's what we then, but we have to capture this into some logic actually, because then we can use this logic to then run into a formal methods, SMT solvers, which is then exhaustively looking at all the different instances of that problem. Right, so but we can capture this, say the vehicle is going through the right lane, it has to go through the right lane and turn in t seconds. So it has to get into its position. That means the steering angle has to be greater than this, acceleration has to be greater than that, unless the right lane is occupied. And then we can refine what this means for this vehicle to do a certain maneuver, and we write that in this certain logic over here. And I'll explain this a little bit more if we have a little bit of time later on. But so then with this logic now, we can then specify all of these different driving scenarios and behaviors with all of these agents to then make sure that they don't get into a accident or a crash scenario, right? So the way we do this is now with a tool development where we have a scenario definition language to describe the scenario and how these vehicle, the topology over here, the traffic laws, the vehicles in discrete states and continuous states, the vehicles planners, and how the vehicle is actually behaving. And for that particular scenario, how is it going from speed, headway control, speed control. So all of that is described in a hybrid model of this vehicle for, say, like an exit scenario, right? So, and this is all very easily specified with this scenario definition language, and then we can start to test this scenario using our testing engine, which is essentially going through these rounds and are finding the place which is the lowest robustness, and then the cases which are in very low robustness, which we cannot eliminate with testing, we basically send that to our verification engine over here, which then exhaustively looks at just that small range of problems, and then that can allow us to eliminate even those smaller issues and clearly identify what's unsafe behavior. We can introduce computer vision code as part of our testing tool and black box systems within the testing. So you can basically plug in off the shelf or any commercial vehicle system into this tool chain to be able to capture that, right? So, and then this allows us to then run through this, and that's sort of the engine that is sitting behind this. So you may not have understood maybe like more than half of what I was saying in terms of the logic, but essentially this is some way of specifying the behavior of all these vehicles. So it's a behavioral specification language, but it's a formal language of specifying that, which can then be used in these verification engine tools to then eliminate all of these or determine safe and unsafe cases very explicitly, right? So let's look at, well, you can say, let's look at using, the simulated world. You'll be like, well, it's different from driving in the real world, of course, right? But nowadays with simulated worlds, we can get to it's very hard to say what's real and simulated over here, and that is simulated right on the top. But so if you look at the distribution of like spatial information and colorfulness with all these different actual real world image data sets, then the blue one that is behind, that is our simulated world data set, and it's basically within the same distribution. And in terms of the performance of the algorithms using the simulated data set, they actually perform slightly worse with the simulated data set than with the real data set. And so our results are a little conservative in that sense, right? And it is a first step to safety. It's not saying that a car is going to be totally safe as soon as it gets on the road because it drove really well in the simulated world. Lots of studies have shown that if you train on simulated driving and real driving, it's better than just training on real driving only or simulated driving only. So you have to complement that, right? There are many open problems in terms of how does weather affect this thing, how does uncertainty propagation go from sensing and the perception side to making errors on the control side, but I'll leave that for later. So but now this method of picking these scenarios is a little bit artificial, right? I picked a T-junction, I picked these scenarios, because they were the riskiest scenarios from this NHTSA report over there. But what we really want is not like just a generic T-junction scenario. We want that T-junction that's down over there, right? We want to see how will an AV actually drive based on that T-junction. So we start to use DOT cameras now. So we can take DOT cameras, and then from these cameras, we can actually then extract and do object detection and identification of the vehicles, and then we can actually play back this in a simulator. So I took that from that video, we made it into a simulation, and then we can basically extract now the driving behavior from that actual drive over there, and then use that to train a naturalistic driver, right, in that environment. But I'm not just training another driver, and what I want to do is I want to replace some of these cars with my AVs. So you can see that AV is driving a little risky over there, right? But that AV is now reflecting some naturalistic driving behavior, but it's using its LiDARs, it's using its perception engine, etc., to then drive pretty similar to how these vehicles are driving in that T-junction case over there. And so that we are using this sort of approach called imitation learning, right? So it is an approach where it is really basically getting trained from many different examples over there. But then we also run it through a discriminator which eliminates non-naturalistic driving behavior through that. So then for that same highway, if this is a real image of IAT over there, we can then run this in our rendered system. But what we really want to do now is we got naturalistic driving behavior with an AV within that same driving scenario, and then we can see the distribution over here of the naturalistic driving behavior. And what we really want to see is where are the aggressive driving on the tails of the distribution. So we are really trying to do this rare event simulation and capture the most aggressive driving scenarios. And so then I can now play this back and run experiments by shifting the mean of where I'm operating within that distribution to more aggressiveness. So, and that will help me capture, well, there are no crash situations here, or there is a rear end crash over there. There is a side swipe crash, and then different kind of crashes. But essentially, I'm now driving with all the other vehicles are following that naturalistic driving behavior that we trained on that situation, and then our AV is driving through the same situation, but we are getting more aggressive traffic by changing the mean of running that. And that allows us to now speed up the capture of these unsafe conditions from 2 to 20 times faster than Monte Carlo methods. And this is a very scalable approach. So the idea is, can we now replicate this for all DOT cameras, and then actually then see how AVs will actually perform, at a city scale, rural scale, and so on, right? So we use a lot of models, right? And then, but we have to be careful in terms of how we use them, where do we use them a lot, right? So and then we also build like now real cars where we want a lot of our students to know how the whole system actually works. And while many companies, many universities have these cars, it's really important that everyone coming through our program can actually know how to build an AV. And so the nice part is our Penn campus is somewhere in that corner over there, and we have a new extension of our campus in the city of Philadelphia, which is a 23-acre campus, and this is basically like a city, a little district that we can drive through and around. This is also like one of the world's largest drone centers with cameras. So there's a lot of experimental research that we can run here, and that's where we drive our AVs for closed circuit testing over there, right? So as part of our DOT center, last month we actually, last month we had a next generation trucking summit where we were looking at all these issues of, how does autonomy is coming first to these trucks, electrification, platooning, and so we had a lot of the national transportation experts come down to talk to us about that. How is it affecting employment? And so both technology and policy issues, and that was a very interesting sort of summit. Something fun that we do at Penn is also we build these F110 racing cars, right? These are Formula One racing cars. They're 1/10 the scale, but they're 10 times the fun. And so these are this size cars, but they're fully autonomous cars, right? So, and we basically teach everyone how to build, drive, and race these systems, and to run these systems, from perception, planning, control. And we have online lectures. Everything is open source, right? On this this F110th website, you can just go there if you're interested in that. And then I think this is probably a good time to just put the audio on. So then this is sort of one example over here where, yeah, that's right, isn't it? Where these cars are now running their sensors, actuators, with LiDARs, depth sensors, all on board, right? There is no laptop involved. It's making all of its decisions in the. So this shows you like the LiDAR map of how it's making its way forward, doing overtakes and So here the idea is that the objective is to go beyond making the vehicle as safe as possible, but to really be pushing the boundaries to the limits of control and perception. And as part of our work, we also every year we have two of these Grand Prix competitions. This was one in April that we had in as part of the Cyber Physical Systems Week, and where now we have groups from all over the world actually come in based on the same reference platform. So it's not like you can spend more money to get a better. This is actually a sophomore undergrad student. So the whole idea here is how do we actually, build like this department of autonomy, right? And in not just with vehicles, today it's vehicles, but it's autonomy in more general, and to learn about perception, planning, control so this is also a battle of algorithms over here, where they all have the same reference car, and then they are trying to race it head to head with other teams like that, right? So I'll just forward this a little bit, but so this is a vehicle that's making all of its decisions on board. So we don't have much time for the second part, but I'll give a very brief overview of another project that we work on is building this urban air traffic controller for different drones, right? So I'll give you just the 2-3 minute version of it. But essentially, say suppose you have in a city you want to be able to fly 500 plus drones right over Manhattan. How do you organize that airspace, right? So say you want to make sure that there's some geofenced zones over there with no fly zones, and the certain drones have certain pathways they want to go around because they want to patrol those areas, or they want to get extract some information. So say like AT&T, for example, wants to monitor some signals in certain spaces at certain times, and say Amazon wants to do some delivery at a certain point. Drones, by the way, are the worst platform for deliveries. So never use that example if you ever do, because they just cannot lift weight, right? They're not designed for that. The physics is against it. Um, so whatever Amazon says about drones delivering, goods is just a PR stunt. So how do you organize this airspace? But in that organized airspace, how do you make sure that these drones can satisfy spatial, that means get from A to B, temporal, get there within a certain time window, and reactive constraints, right? Reactive is how close do you get with other drones. And so the goal of this project is to look at these multi-drone, multi-mission systems, but to automatically synthesize, given these plans, trajectories, and path waypoints for all of these drones to satisfy all of these missions, right? So say they have to satisfy spatial, respect geofences, and maintain minimum inter-drone distance over there. They have to basically complete their mission within a certain time window, and then get on to the next part of the mission. They have to make sure that they do this in an energy efficient manner, and that they also have to basically be within these time windows for each of the parts of the mission with that, right? So you want to sort of make sure that say if to one set of drones wants to patrol these two regions over here, and another set of drones has to go from the base to do a delivery. How do we, and they have some sort of unsafe region over there that they have to avoid. How do we organize many of these drones to do that, right? So this is an example of how we can organize all of these drones to satisfy their spatial, temporal, reactive mission goals, and ensure that they can finish them in time, and but determine what kind of flight paths they should be taking. And at the same time, things can go wrong once you decide what to do, and how do they recover from that, right? So, and then this is actually them all working within this lab to sort of keep to do that same kind of mission for real. So this is running on board on all these drones for different types of missions over here, right? So it's hard to see in this resolution, but essentially they are all trying to get into from different starting points. They're all trying to get into this goal region, but they don't crash into each other. When they come into the goal region, they move a little bit out and they make room for each other. But the whole point is that these missions can now be specified at a very high level, right? On an iPad, you just draw the mission, do patrolling, do this delivery, etc., and say like deliver a package to this location in the next 5 to 10 minutes. And then it has a list of scenarios that it's going to go through. It's going to take off, hover, going to actually navigate through that, and then it has to return to the base. And you have some set parameters in terms of your safety parameters. And so what we do then is we map all of this automatically to our logical behavioral logic over here, just like in the earlier case, but we use a different type of logic over here, and then we synthesize all of these trajectories. So with just a push button, we can take 50 drones and then basically automatically schedule them all to do all of their separate missions, not crash into each other, and succeed in the missions while maintaining safety. And they can be deployed on actual drones, both indoor and outdoor drones for real. And the idea is, how do we make sure that they have the maximum robustness, right? The same idea as we had before, that they can allow for a lot of disturbances, whether it's wind, whether it's a drone falling through the sky because it's run out of battery or had a malfunction, or whether it is some rogue nodes coming through the network. This is a very robust sort of system over here. So I won't go through all of this, but I'll just give you an example of how we explain it, and then I'll stop there, right? So if we want to sort of decide how to use this logic, we want to say, well, this drone over here should never get into this unsafe region because this is a no-fly zone over here. So we can have a logical formula for that to say that this is an always symbol over here, that this zone should never get into this unsafe region. This is an so we have an always operator saying that through the lifetime of this mission, this zone should never get there. And there's a temporal range that the lifetime is from 0 to 10 time units. And then there's a logical negation that means you should never get into that region. And this is some atomic proposition saying that this is the unsafe region for, and this is for what drone 1 should satisfy. Similarly, for drone 2, then we can just AND that, and we can concatenate that condition over there with a logical AND, right? And then we can say that, well, these drones should also between themselves keep some minimum separation, that the distance, the norm 2 should be more than this distance over here, right? So then we can say eventually these drones should reach that goal, and so then this is an eventually operator. So this is another symbol that is basically saying that within this time region they need to get to that goal. And then same thing for drone 2, right? It should get to that goal, and then you would say like an until operator. So and this could also sort of imply something, that once it gets to its goal, is dropping off a package. So if then else conditions can be captured in this sort of and so then we can start to say, well, now this is sort of our property, that these drones should basically avoid this region, get into this, get to this goal over here within this time, and then they should also maintain some minimum speed until they get to the goal, and then they can actually stop there, right? So we can concatenate all of these properties that they have. This is all very logical and abstract, but then it basically is something that we can, since it is based on a certain semantics of its logic, we can then use that to synthesize these actual trajectories from that, right? So, and this is sort of our tool that we then can use to generate all of these missions. And so what I'll do is I'll just skip forward to the last part of where these missions are then finally planned, right? So essentially what this system is doing is taking all of these multi-drone missions that are, whether it's for agricultural stuff or surveillance, whatnot, right? So we do not work on any defense projects, so it's all just peaceful projects. So but then that gets mapped automatically to a specification, and then from this specification it takes into account the control constraints, because the drones cannot fly in certain ways, and they have to go into smooth splines, and so they satisfy this continuous control capability to then generate the control actions along a certain set of waypoints. So essentially the output of our tool will give certain set of waypoints for all of these drones to take at different velocities, and then they satisfy getting from waypoint to waypoint with their control constraints, and automatically we can generate these complex missions over here. We can do this in a very efficient manner, where we can do this online for about half a dozen drones right now, and then in a distributed manner we can do this also in a very good way, where we can maintain safety, maximize robustness, to say basically whatever disturbances the drones are going to go through, this is a pathway that maximizes the robustness, and then we can do this calculation in an online manner now for a fleet of drones as we go through that, right? So this is essentially like combining controls and formal methods to basically then work with these physical systems, but at a large scale, to be able to generate then mission planning. So it's kind of a crossing the boundaries of a lot of things, from robotics to formal methods and computer science to capturing dynamics of the system. And the current work is really looking at how do we do this in a very distributed fashion, and where we can replan if there are changes like weather changes, or there are emergency landings that are happening. Another extension is that we are working with Amazon Robotics to basically then do robots that are fetching crates and pallets from the docks into their large Kiva based robotics based warehouse systems, which are just running on a grid like that, right? So how do we actually navigate and get these bots to come in and out of the warehouse, go around humans, and so on? It's a very messy problem there. And then we have some undergrad group that is actually developing this whole app now that can go end to end, from specifying different missions to flying a dozen drones in that outdoor space that I showed you over there. So I'll stop here, and I can take any questions if you have on whatever we spoke here. Thanks.